Synthesis and characterization of photovoltaic cells sensitized with CIS and CdS quantum dots. Introduction. With the increasing demand for energy in industry and households, new ways of obtaining energy from renewable sources, such as sunlight, have been developed. Photovoltaic cells serve as crucial devices capable of converting solar energy into usable electricity. Among the various generations of solar cells, first, second, and third, the third generation introduces advancements such as the utilization of quantum dots for sensitization. Some of these cells are currently based on cadmium sulfide, CdS, which, although they have attractive efficiencies and are low cost, can be a threat to health and the environment. Objective. This study aims to explore a more sustainable alternative by employing green quantum dots composed of copper, indium, and sulfur, CS, to analyze whether the efficiency of solar cells is affected by the order in which the materials are incorporated by combining CdS and CIS to optimize the solar cell. Methodology. First, the FDO is washed with soap and water. Then it is placed in an ultrasonic bath with acetone ethanol for 15 minutes. Next comes the compact layer, which is deposited by spray pyrolysis technique, which consists of the aerosol atomization of a precursor liquid on a hot surface, where it is converted into an oxide, TiO2. Once the process is completed, a layer is achieved that prevents direct contact between the electrolyte and the FDO, thus preventing possible leakage. Then the transparent and opaque layers that make up the mesoporous layer are deposited by screen printing technique. The transparent layer is deposited first, which provides the surface on which the CdS quantum dots generated by the Seiler method will grow. Then the opaque layer is deposited. This layer serves as a tool for the dispersion of the light passing through the transparent layer. This dispersion is beneficial because it will increase the possibility that the incident light is absorbed by the sensitizer. As a photogenerator are the CIS and CdS quantum dots, which are deposited by the Seiler method as follows. For the CIS quantum dots, the sample is first dipped in the indium acetate precursor, then allowed to drain out of solution, then dipped in an acetic acid water solvent, which acts as a remover of excess ions, then dipped again in the copper acetate precursor, then dipped again in the copper acetate precursor, then it is immersed again in a deionized water solvent. It is allowed to drain. Again, then it is immersed in the sodium sulfide precursor. It is drained again, and finally it is immersed in the methanol water solvent, and it is allowed to drain out of solution. This whole process is considered as a complete cycle for CIS quantum dots. For CdS quantum dots, the sample is immersed in the cadmium acetate precursor, then allowed to drain out of solution, then immersed again in an absolute ethanol solvent, drained again, then immersed in the sodium sulfide precursor, allowed to drain, and finally immersed in the methanol water solvent. For the whole selective electrode, there is a polysulfide-based electrolyte. What is achieved with this electrolyte is to obtain an appropriate redox couple. A Cu2s counter-electrode was used as cathode in order to correctly catalyze the reduction reaction of the electrolyte. At the end, the cell is assembled as follows. A drop of electrolyte is added on the counter-electrode, then the sample is placed on top of it and characterized. Results. Samples were made with CdS-CS and CIS-CdS configurations, with 8 fixed CdS cycles and varying only the CIS cycles by 1, 3, and 5. Table 1 shows the results of the photovoltaic parameters. The first 3 samples with the CdS-CS configuration shows that there is no linear behavior in these results. Starting with the sample with 1 cycle of CS, it is seen that the current decreases when increasing to 3 cycles, and when increasing to 5 cycles it rises again, as can be seen in Figure 8 of the JV curves, pink curves. where this inclination is seen in the line indicating shunt resistance due to possible leakage problems. That can be corroborated in the IPC curves in Figure 9, where in the sample with one cycle of CS you can see its absorption range, and by increasing the cycles to 3, it is observed that it expands its absorption range and has more external quantum efficiency. But in the end, this extra absorption is not reflected in the current. On the contrary, which means that there were more losses than were gained by this absorption, then it is increased to 5 cycles, in which increases its external quantum efficiency and the absorption range compared to one cycle, so it absorbs enough light to overcome these losses and the current rises, but does not reach the first sample. For voltage, it can be seen in Table 1 that it is decreasing a little, where it can also be seen in the JV curves in Figure 8, which could indicate recombination problems. Being the best sample of this configuration with one cycle of CS with an efficiency of 0.69%. For the CIS-CdS configuration, it is observed that just like the previous configuration, there is no linear behavior in these results, starting with the sample with one cycle of CS in the current. When increasing to 3 cycles, it goes down, and when increasing to 5 cycles, it goes up again, as can be seen in Figure 8 of the JV curves, blue curves, where this inclination is seen in the line indicating shunt resistance due to leakage problems in the samples with 3 and 5 cycles, being the sample with one cycle the one with a higher current. This can be corroborated in the IPC curves in Figure 9, where in the sample with one cycle it can be seen that it has the highest efficiency. When increasing the cycles to 3, it is observed that it extends a little its absorption range, but has a lower external quantum efficiency, so it has less current. Then it is increased to 5 cycles, where it is seen that it increases its external quantum efficiency and extends more the absorption range and manages to increase the current, but it does not reach the first sample. For voltage, it can be seen in Table 1 that when adding 3 CES cycles it decreases, then when adding 5 cycles it increases a little, but like the current, it does not reach the sample with one cycle. This decrease in voltage could indicate recombination problems. Being the best sample of this configuration with one cycle of CS with an efficiency of 1.42%. In general, it can be seen that the best configuration for all photovoltaic parameters is the CIS-CdS configuration, achieving twice the efficiency of the CdS-CS configuration. Conclusions. The sequence of material incorporation has a significant impact on the photovoltaic parameters, highlighting that the CIS-CdS configuration offers superior performance with twice the efficiency. By increasing the number of CS deposition cycles, the absorption range is extended.